This is part 2 of 17.6 surface integrals. We just finished finding the surface integral that was needed to find the surface area of a torus, and now I'm up to page 6 of the notes here, where I have example 5. Suppose the temperature on a sphere of radius a varies according to this function. These are some weird input variables. There's 2 of them, and we're talking about a surface. So this is probably the parameterization of our surface. T of phi theta is 10 plus 50 sine phi. Okay, so this phi and this phi are the same thing. They represent the latitude in spherical coordinates, where 0 degrees is the North Pole, and pi, 180 degrees, is the South Pole. So this is saying the temperature of the sphere is given by this function, and we're looking at the entire sphere, all the way from North Pole to South Pole, and all the way around longitude-wise. Find the average temperature over the poles. The average temperature over the poles? I don't think that's what I don't think that's the intended question. I think we want the average temperature over the whole sphere. If you want the average temperature over the poles, then you don't need an integral at all. You would do the North Pole, which is phi equals 0, and you'd get 10 degrees. And then you do the South Pole, which is phi equals pi, and you'd get 0 again, so you get 10 degrees. So the average temperature over the poles is 10 degrees. So I don't think that's the question we intended here. I think we wanted the average temperature over the whole sphere. Well, how do you find the average of anything? To find the average, you integrate all the little pieces of it along the entire surface and divide by how much of the surface you have. This average formula was the same kind of formula when we had the average over an interval. You did the integral, and then you divided by how long the interval was. Or the average over a region is you do the double integral of the function, and you divide by the area of the region. Or the average over 3 dimensions is you do the triple integral, and you divide by the volume of the region. This is a surface S, so we're going to divide by the surface area after we do the integral. This function, t, is going to be in here in the integral. Okay. One thing is that the surface area is often an integral itself, but here I have a sphere of radius a, so I don't have to actually do an integral to find the surface area of a sphere, because the surface area of a sphere is 4 pi r squared. So the surface area here is just 4 pi a squared. This double integral, this is a surface integral. It's not a double integral over a region in the plane. It's a double integral over an entire sphere. So to do this, we have to switch to a parametrization of the sphere. Then you can do an integral over the region that comes from your parameters. So this t is still going to be in here. And then to switch ds into du dv, I need our familiar friends tu cross tv. Okay, well, what are going to be my u and my v here? Since I'm talking about a sphere of radius a, I'm going to think spherical coordinates. Where the radius of the sphere is a, and then I have theta and phi. I'll just let theta be u and phi be v. And then my parametrization can be r of uv, is the standard spherical parametrization of a sphere, which we figured out before. Does it have cosine u and sine v, or cosine? I'm going to draw it. You could look up the formula for what x is in spherical coordinates. It's easier for me to remember how it works by drawing triangles. So x is r cosine theta, but r is rho sine phi. So it's rho, here's rho was a, I'll just write it in rho phi and theta first. So it's rho sine phi cosine theta, rho sine phi sine theta, and then rho cosine phi. But I have new names for rho, theta, and phi. Rho is a constant A. Phi I'm calling V, and theta I'm calling U. And my bounds, well, theta goes from 0 to 2 pi. And V goes from 0 to pi. So this is my parameterization. I can use this parameterization to find Tu, the tangent vector in the u direction, and Tv, the tangent vector in the v direction. Then I have this temperature function that I'm also integrating. So this temperature function is going to end up in my integral. Okay, let's get this Tu cross Tv stuff out of the way first. Tu is the u partial derivatives of my parameterization. So I'll get minus a sine v. Do I already know what this is? Isn't it rho squared sine phi? It is. I'm not doing this. We already know how spherical coordinates work. The Jacobian for spherical coordinates is Tu, the size of Tu cross Tv is rho squared sine phi. We did this like several chapters, or maybe one chapter ago, which is going to be a squared sine v. If you did Tu and Tv and took the cross product and took the magnitude of the cross product, you would get this. This is just the way of getting the Jacobian for any old weird parameterization. If you're using the standard parameterization for spherical coordinates, then you already know what it is. So let's get the average temperature going here. It's going to be 1 over 4 pi a squared. My integral is now a uv integral. So the outer integral is a v. V goes from 0 to pi. The inner integral is a u integral, 0 to 2 pi. T is 10 plus 50 sine v. That's capital T. And then this Tu cross Tv's magnitude is a squared sine v. And then I have du dv. Okay, looks like I'm going to have a sine squared v integral, but the first integral is a lot easier. The inner integral is a u integral, and there's no u's in here. So this integral just multiplies by 2 pi, which means I cancel the pi and cancel one of these, half of this 4, and I have 2a squared, and then I just have the v integral remaining. Wait, this a squared is a constant. Let's cancel it with this a squared. And then I guess I can just factor out a 10 here. So I'll have 1 plus 5 sine v dv. Okay, so this will split into 2 pieces. 5 integral of just sine v, and then 25 integral of sine squared v. Let's finish this. The integral of sine v from 0 to pi, I feel like it's 2 or something. Let's just get it. So this is going to be minus cosine v from 0 to pi. That's 5 times minus 1 minus 1. Yeah, it was 2. So this part comes out to 10. This part, the integral of sine squared v, my easiest way out of integrating sine squared v is to use the power reducing formula. Sine squared v is half of 1 minus cosine of 2v. This is just a trig identity that if you've done Calc 2 recently, you've had to use before. Then I can get this integral. It's v minus half sine 2v from 0 to pi. Plugging in 0 or pi into this sine term is going to give me 0, so it doesn't do anything. So I just have a pi here. So this is my final average temperature. The average temperature over the whole sphere is 10 plus 25 pi over 2 degrees. Cool. Make sure that this is what I thought I was going to get. I thought I was going to get approximately 50. Let's make sure this is approximately 50. 25 pi is like 75, maybe 80. 80 over 2 is 40. Yeah, okay, so this is about 50 degrees. Cool. So I had my temperature varying over the surface of the sphere. It was 10 degrees at the poles, and it was warmer at the equator, right? If phi is pi over 2, I got 60 degrees. So the temperature was varying from 10 up to 60, back down to 10. And because there's so much more of the sphere around the equator, I end up with an answer that is closer to 60. It was about 50 degrees. The key thing to do here, as with all surface integrals, is figuring out the magnitude of Tu cross Tv. Magnitude of Tu cross Tv is something you can always calculate directly using your parametrization, but it's also good to remember that it's the Jacobian. So if you're using a standard change of variables that has been used a million times before, like if you're doing the polar one, then the Jacobian is r, because dx dy is r dr d theta. If you're using the spherical coordinates, then the magnitude of Tu cross Tv is rho squared sine phi, just from the spherical coordinates section. Yep. Onward. Okay. Let's say instead of having a surface that you've parametrized, what if you have a surface that's given by a function? This is how we started dealing with surfaces at the very beginning of the class, where you would have your input was a point in the plane and your output would be the height. This is called an explicitly defined surface because it has a formula for x and y. The key thing here is that makes it really easy to parameterize. You can just use x and y as your parameters. So your surface will be r of uv is, well, what's x? X is x. What's y? Y is y. And what's z? It's this function. So when you go to calculate, like if you have this surface that's defined explicitly, then we can figure out what is Tu and Tv and cross them to figure out what the Jacobian is, like once and for all, without having to do it over and over. So what is Tu? Tu is the u partial derivatives of this thing. So it's going to be 1, 0, gu. And Tv is 0, 1, gv. So when I go and find this normal vector by doing the cross product, well, what is the cross product of these two vectors? Let's just figure it out. 1, 0, gu, 0, 1, gv. I'll do the trick where I repeat the first two columns and then do the forwards diagonals minus the backwards diagonals. The forward diagonals are 0, 0, and 1k. And the backwards diagonals are 0, minus gu in the I component, and minus gv in the j component. So, I mean, we're switching back and forth between u and v a lot, but just to, like, u was x and v was y. So when I go and actually write down this cross product, I'll just write it in terms of x and y so we don't have all this unnecessary u's and v's. It's going to be minus gx minus gy 1. So that's our Jacobian. Oh wait, this is just the vector. The Jacobian would be the magnitude of this vector. So that's square root of gx squared plus gy squared plus 1 squared. So that's our multiplier, our factor. That's going to go in our integral. So if your surface is defined explicitly by a height function, then you get to just use this. You don't have to find Tu cross Tv and take its magnitude every time. So we'll just say that if you're integrating a function over a surface, then you can just put the function in here. And then where you should have Tu cross Tv's magnitude, we say, yeah, but I remember what it is. from this calculation up here. And then this is dA. It can be either dx dy or dy dx, whatever you want. Could it be r d theta? I guess it might be able to. Anyway, you can find the surface area of an explicitly defined surface by just doing this surface integral without the f. So this is just, it skips some steps that are, it skips the most obnoxious steps if you're dealing with a surface that's defined this way by a function of two variables. So let's do one. We'll find the mass of some surface. It's the first octant part of this plane. And it'll have this density function. Okay, well, how do you find mass? To find the mass, you should add up all the little bits of mass. But mass is found by the amount of the thing times the density. So it's going to be the density times how much of the surface you have. So this is a surface integral. And the surface is like, we can write the surface explicitly by solving for z. You do 6 minus x minus 2y and divide the whole thing by 3. So this is my surface. And if you can write your surface explicitly, then that means that you can use this like cheap formula where you don't have to do any cross products. So it's pretty nice. So this is going to be the integral over just x and y, an x and y region of your function times this scaling factor, the x, the x partial derivative of your function squared, plus the y partial derivative of your function squared, plus 1, all square rooted. Well, the x partial derivative is minus a third. The y partial derivative is minus 2/3. And there's a plus 1 in here. So whatever this number equals, it's some number of ninths. It's going to be 1/9 plus 4/9 plus 9/9. That's 14/9. And I'm going to square root the whole thing. So I'll get square root of 14 over 3. And I can factor that number out. You can't always factor the number out. You can't always factor out the Jacobian. Sometimes it has x's and y's in it, but in this case it does not. Okay, what's missing from our integral is we haven't decided yet how we're going to deal with the base, like the region in the xy plane. If that region ends up being a circle, we might use dA equals r d theta. If that region ends up being like a rectangle, we'll use dx dy or dy dx. Let's see what the region is by looking at the shape. So here's my xy plane. The xy plane, what is the xy plane? The xy plane is the place where z is 0. So the important boundary here is x plus 2y equals 6. That's just a line. If y is 0, then it says x is 6. If x is 0, we get that y is 3. So here's my region. The top boundary here is a line. I can solve it for y, I guess. Y is going to be 6 minus x all over 2. And this is my region. That helps me decide how to deal with dA. dA, since this has basically got right angles and straight lines, I'm going to use rectangular coordinates. So I will say that dA is dy dx. This lets me say what the x bounds are as numbers from 0 to 6, and the y bounds in terms of x, so the bottom function and the top function. The bottom function is y equals 0. The top function is 6 minus x over 2. Now the integral is all set up, and we can find it. And this is the mass of this planar surface that has variable density. Outer integral waits for us to be done. Inner integral is a y integral, so I get x squared y plus a third y cubed from 0 to 6 minus x over 2. I feel like I made some mistake here because not like it's wrong, but like I made a strategic mistake because I don't like this, having to plug this in for y. Anyway, plug this in for y. I get x squared times 6 minus x over 2 plus a third 6 minus x over 2 cubed. Ugh, I'm so uncomfortable. Okay. Is there any nice way to do this? I don't really think so. This one I can multiply out. So I'll have 3x squared minus half x cubed. This one, I don't think it's useful to multiply it out. These early integrals I can just do. So the integral of 3x squared is x cubed. The integral of half x cubed is an 8th x to the 4th. And the integral of this thing is, well, keep the constant. Can I scroll over it? Ah. Keep the constant. Make the power 1 bigger. Divide by the new power. So instead of a third, it's going to be a 12th. And then because of the chain rule, I'm going to be off by minus a half here somehow, and I'll have to fix it. So what is the derivative of this? I'm trying to do the integral of this like without doing a u substitution. Maybe it's a mistake, but I'm doing it anyway. So if the integral of this was this, then the derivative of my result would be in the integral. So what is the derivative of my result? The 4 would come down, which makes the 1/3. The power would reduce by 1, which would make it cubed, and then I'd multiply by minus a half. So I am off by minus a half. I guess that means that if I made this, if I put in a -2, it would come out correctly. To factor the minus a half that's about to pop out. Because now the 4 would cancel with 12 and make a third. This power would go down, which would make it cubed, and the minus a half from the chain rule would cancel this -2. Yeah, this works. Okay, so let's plug in 6. Uh-oh, I don't know 6 to the 4th. This is very silly. I don't know what 6 to the 4th is. This is a total mess. We've done almost all the work, though. Okay. 6 to the 4th over 8 is 162. And then when I plug 6 in for x here, I get 0. And then I need to subtract what happens when I plug in 0. I get a 6th times 3 to the 4th. One 1/6 times 3 to the 4th is 27 halves. I don't know. I don't know that I'm really accomplishing anything by getting the exact value here, but we're doing our best here. So this is 54 plus 27 over 2. So I have 108 over 2 plus 27 over 2. What is 108 plus 27? That's 135. I feel like 135 is divisible by 3. I'm sorry. I don't know. 135 divided by 3 is 45. So I have 45 root 14 over 2. Okay, we can get lost in the weeds dealing with the numbers all we want, but that's not the point. So let's just try not to worry too much about the specific numbers. What was important is that we were finding the mass. The mass should be found by adding up all the little bits of mass, and mass is density times surface area. That tells you that you're doing a surface integral with this density function as your integrand. then you see that your surface, you need to either parameterize your surface or notice that your surface is explicitly defined by a function. And that this page was about, if you can solve your surface for z in terms of x and y, then you just get to use this formula, which is simpler than the like tu cross tv thing. In that case, you get everything in terms of dA like immediately, and then all the work you have to do is the work from the double integrals section, which was, I don't know, long ago at this point, which was look in the xy plane to get your bounds. Then the integral ends up being a total mess, but whatever. Okay. Hopefully you got the point, even though we spent a whole bunch of time on the stuff that wasn't important. Okay, so what are we doing? So we did the surface integral of a function. When you had a surface and there was a function defined on the surface, we were able to do the surface integral of the function. We did this with line integrals too, where we started by doing the line integral of a function. After that, we then went ahead to doing the line integral of a vector field. And similarly, we're going to do the surface integral of a vector field here. And that will turn out to be like more useful in general. So first we need to get some like bookkeeping out of the way, which is that a surface that we're going to do an integral of a vector field with has to be orientable, meaning that you have to be able to say that like one way of the surface is the outside and one way is the inside, that there's like, that it's got two sides to the surface. If you make a Mobius, I never learned how to pronounce this character correctly. It's more like so the Mobius strip, I think, is a non-orientable surface. It's a surface that only has one side. You can build one of these really easily. You take a strip of paper. Do I have scissors? That is the question. I do have scissors. Okay, take a strip of paper. If you just take the two ends of your strip of paper and you connect them together, you get a cylinder. And this has an inside. Like if I walk this way, I stay on the inside, and an outside. If you instead take one of your ends and you twist it before you attach it, then you get a Möbius strip. And the problem with the Möbius strip is that it doesn't have two sides. If you start walking on it, if you like draw the beginning of a path on the Möbius strip, what will happen is that you will cover the entire thing, including what you previously thought of as the other side. So a Möbius strip is kind of like a screwed up surface. It's not orientable. We can't orient it. We can't decide that it has an out and an in. So we won't be able to deal with that kinds of things, with those kinds of surfaces. A sphere, we can like coherently decide that like that way is up, like that way is out of the surface. So as long as you can, as long as it's possible for your surface to have an outside direction and an inside direction, it's orientable, and you decide which way is out. Once you've oriented your surface, then you can like take your surface and drop it into a vector field, which remember in 3 dimensions, our like idea of a vector field is that at each point in space, there's wind, and wind has a direction and a magnitude. So that's a vector at each point. So we can try to figure out what's the flow of the vector field, across that surface. So now we're thinking of our surface as like a sail in the wind. We're saying if the wind blows and this surface is like catching the wind, how much wind does the surface catch? We do it the same way we did it in the 2D version, which is to catch wind, to have flux through a surface, you check how much F agrees with the normal vector n. So how do you find out how much a vector agrees with another vector? You find out how much a vector agrees with another vector by taking their dot product. So the flux integral for a surface to figure out how much of the vector field is captured by like flux through the surface is the surface integral of f dot n. So this will be my flux integral in 3 dimensions. The main challenge here is that we will need a normal vector n to dot with. So how do we do that? I have good news. The good news is that this normal vector n, well, how do you get a normal vector to a surface? You take 2 vectors in the surface and you cross them. So here's my normal vector n. This is going to look real familiar. You just take 2 tangent vectors to the surface and cross them, and then normalize it to make it a unit vector. So why is that good news? Well, that's good news because every time that we tried to do a surface integral before, so we're going to do f dot n ds. Every time we tried to do a surface integral, what we ended up having to do is you'd parameterize the surface in terms of u and v. Then you'd get to actually do your integral du dv, which is what we wanted. But the cost was you had to find tu cross tv and find its magnitude, and that was your like multiplier. So this is like how surface integrals are calculated. But if n actually has this in it, then we get to cancel the obnoxious part of the calculation, and it's just not there. So these cancel, and we get to just do a uv integral. You still have to do the cross product, but there's no like finding its magnitude at the end. So this flux integral can be found by just doing vector field dot tu cross tv with no magnitude calculation. And then your integral ends up in the uv plane. I think I can put this in a box, hopefully. Yes, so here's the box. So suppose you have a continuous vector field on a region, and you've got a smooth surface S in the region, and the smooth surface S has a parameterization. Then the flux through the surface is the integral of f dot n ds. This makes sense because we're trying to flux through the surface asks how much does the vector field, how much does the wind agree with normal vectors to the surface? The calculation on the previous page tells us that this is actually an easier integral than most surface integrals. It's f dot tu cross tv. dA, where dA is du dv or dv du. Tu just means the u partial derivatives of the parameterization. Tv is the v partial derivatives of the parameterization, like we've been doing for this whole section. Yeah, there's a warning here that this has to actually work. Like the normal vector has to be pointing the right way. This is actually kind of important because if you mess this up, then you'll get the opposite of the right answer. Like you'll get a negative answer instead of a positive answer. So careful, basically. Sometimes you'll have to use the opposite of tu cross tv. Tu cross tv is guaranteed to be a normal vector to the surface. So if this is your sail in the wind, tu cross tv is definitely going to be normal, but it might go this way, or it might go it might go the other way. And if the wind is helping you, you want it to come out to a positive number. Okay, if your surface is defined by an explicit formula, like an explicit function, then this tu cross tv is easier. It's the one that we found before. It's, so I'll write the beginning of it again. Still the flux integral. But now tu cross tv is, what was it? It was minus x partial, minus y partial, and plus 1. You could put zx and zy. It's named the function s of xy because we're just running out of variables. It's the x partial derivative of the function that defines the surface and the y partial of the function that defines the surface. So let's get some flux integrals here. So here's my vector field. This is the wind that's blowing around. It's constantly blowing in the positive y direction, but depending on where you are, there's different x and z components. We're gonna make our sail, our surface in the sky here, is gonna be a triangular part of a plane. So can I solve this for z should be your question. Because for surface integrals, if you can solve for z, you get to use an easy version. If you can't solve for z, that's fine. You just use some parameterization and then you put it here. But this one, I solved for z, so I can use the easy formula that the flux is... Easy is not the right word. It's the easier formula. F dot, all this stuff. dA. Sorry. So I'm using this formula. And then I just drop in what f is and what zx and zy are, and then what do I mean by dA? So let's do a little bit at a time. F is this vector field, 2y, 3, minus x. These come from the parameterization of the surface. So here it's the formula that gives us the surface. Zx is minus 2. Minus zx is plus 2. Zy is minus 4, so minus zy is plus 4. And this 1 is just always here. dA, well, I'm going to do the integral with respect to the xy plane. So I'm just going to do dy dx here. Then I need to figure out the y bounds and x bounds. I'll put it off until later. Let's do this dot product. I get 2y times 2, 3 times 4, and minus x times 1. To get the x and y bounds, let's just draw the picture. The x and y bounds are in the xy plane, which means z equals 0. So I've got this equation of a line. 8 minus 2x minus 4y equals 0. I can solve this for y. Is solving it for y the easiest way to get a picture of it? I'm not sure. Well, I'm going to solve it for y. So I'll add 4y over to the right side and then divide by 4. I get that y is 2 minus a half x. So it starts at y equals 2 and goes down with a slope of minus a half. This is y equals 2 minus a half x. And the region is this one here. So this is my region R. The x bounds on the outside are just scalars, because scalars, they're just numbers, because the outer integral should be just numbers. Here x goes from 0 to 4. The y bounds can be functions in terms of x. It's the bottom function, y equals 0, and the top function, y equals this line. Then I've got my integrand, dy dx. Then I can just do my double integral. Let's remember what it is that we're doing here. What we're doing is we're finding how much the wind blows into this sail. And we're doing it by saying, look, just do the dot product of the force of the wind with a normal vector to the sail. That'll tell you how much the wind is blowing perpendicular to the sail, which is how much wind flux we actually get. Then we do this clever switch of variables down to the ground, down to the xy plane, which is the point of this section, really, is that it's possible to do this. Then it turns out that the integral is just a not very scary double integral. So we'll do the inner integral first. The outer integral will just wait for us. This is a y integral, so we'll have 2y squared plus 12y minus xy. I said xy and then wrote something completely different. These are the y bounds, so I plug these in for y. Here we go again with the 12 times 2 minus half x, and then minus x times 2 minus half x. All this is dx. I don't want to do this. This is such a bad finale to the problem. The numbers are going to come out nice too, because it's all like 2s everywhere. Whatever, we'll just do it. Okay, 2 times, let's square this out. First term minus 2 times the first times the second, plus second term squared. This 12 we can distribute. This x we can distribute. Oh, it's not going to be nice numbers. Here's a cubed. So what are we integrating? It's 8 minus 4x plus half x squared plus 24 minus 6x minus 2x plus half x squared. Collect all the terms. 8 plus 24, that's 32. Collect the x's. I have minus 10 minus 12x. And collect all the x squareds. There's just one x squared. So in total, I've got 32x minus 6x squared plus a third x cubed. Plug in x equals 4. I'm just barely out of space again. Plug in x equals 4, I get 128 minus 6 times 4 times 4. 6 times 16, that seems like 96. And then I need to add 64 thirds. Fine. So this is 32 plus 64 thirds. So that's 96 thirds plus 64 thirds. It's 160 thirds. I guess I should budget my space like just slightly better, and then I would get to have the answer in here. This is a lot of calculating. Let's ask a calculator to do the calculating part for us, just to make sure I got it right. So I'm trying to integrate from 0 to 4 in the x, and from 0 to 2 minus half x in the y's. And I was just integrating 4y plus 12 minus x, I think. And this was dy dx. 4y plus 12 minus x, is that what I integrated? 4y plus 12 minus x, okay. I'm hoping for 160 over 3. Nice, okay. That's a relief. Anyway, the point of this was not all the crazy like integral stuff. The point of this was the setup, which is you can find the flux by doing a surface integral. And if you can explicitly define your surface by a function of z, then you get to do an easy setup with no cross products. It's great. Last page, one more problem. Last page has, let's say that you have a velocity field of a fluid. So now instead of force, our vector field represents like how fast the water is flowing. When I look at a vector field, I like imagine its divergence to see if that's easy to calculate. I think that's probably a good habit to get into. I'm not totally sure. But when the divergence is easy to calculate, which here it is, x partial of that is 2, y partial of this is 2, z partial of this is 1. The divergence is 5. That means that everywhere is like exploding outward. So there's like a source. This is like a spring that's like, not like a coiled spring, but like a water spring that's like shooting out liquid. Okay. We're shooting out the fluid, and the fluid has density 80 kilograms per meter cubed. This is in 3 dimensions, so I don't know what would make this happen. I guess you would like turn on a hose in space or something to have the water like be exploding outward from a point. Whatever. S is a hemisphere, so we're just doing the the bottom half of the sphere of radius 3. Find the flow rate of the fluid across S. So how much fluid is going through this membrane when the fluid explodes outward in this way? Well, let's see. The flux through a surface is the surface integral of f dot n ds. And then to actually do this integral, we have to decide whether it's better to have like some weird parameterization of our surface, or if you can solve for z. This is a sphere, so the weird parameterization of our surface plan is significantly better. Where's our various formulas? Nope. Well, yes, it is this formula that I was looking for. So we'll use spherical coordinates, and the u and the v will be theta and phi for our spherical coordinates. So this is integral over a region R of f dot tu cross tv dA. So you set up your flux integral and you say, well, there's two ways to go with flux integrals. You can either do the one that has the tu and the tv, or you can do the one where you've solved for z. And they're both fine, and they both, I think, lead to the same integral. But it's a matter of which one seems easier at the time. I would recommend that if you're going to solve for z and it needs square roots, that you not do that, and that you use this instead. So we will think our parameterization is that we'll use spherical coordinates, because it's a sphere. The radius is 3. We'll have theta, and I'll just call the theta u, and we'll have phi, which will be our v. In that case, there's like the standard parameterization, which I've calculated from scratch like over and over. When did I calculate it from scratch last time? Is it this one? No. Whatever. If you look back at the spherical coordinates section, you'll be able to find it. The formulas for x, y, and z in terms of rho, theta, and phi. But I'm stuck with these triangles. You're probably sick of it by now. I see it as like powerful to be able to build them from scratch over and over, but like when I build it from scratch the third time in the same section, I start to wonder if maybe I should have memorized the formulas. Anyway, x is r cosine theta, but r is rho sine phi. So here's r cosine theta. And then here's r sine theta. And then z is rho cosine phi. So this is my parameterization, but rho is 3, theta is u, and phi is v. So 3 sine v cosine u, 3 sine v sine u, and 3 cosine v. This is my parameterization. A parameterization should also have bounds. U is theta here. We're going all the way around the hemisphere. But since it's a hemisphere, and we're only doing the southern half of the sphere, I don't want to start at v equals 0. That's the North Pole. I want to start at the equator, which is v equals pi over 2, and go all the way down to the South Pole, which is v equals pi. So this is my parameterization. I can find tu and tv by just computing them. Tu is the u partial derivatives of all these things. Let's write what I'm doing. I'm just take my parameterization and take the u partial derivatives. So here, 3 sine v will just sit here, and then the derivative of cosine u. The 3 sine v will sit here. and the derivative of sine u. And then 3 cosine v is a constant, so its u partial derivative is 0. Then I've got tv. That's just the v partial derivatives of my parameterization. The v partial derivatives leave the u's alone. So this one will be 3 cosine v cosine u minus 3 cosine v sine u and minus 3 sine v. You might be wondering, hang on, last time you had spherical coordinates, you got to skip all this work. Why did you get to skip it? And the reason was that we already know what the magnitude of tu cross tv is. That's this rho squared sine phi from the Jacobian from forever ago. But this doesn't want the magnitude. This wants the actual vector because we're going to dot it with f. So let's get this actual vector. Let's use this trick we had earlier in the section where it's a good idea to factor out scalars if you can. Like these all have a 3 sine v in them. Minus sine u cosine u 0. And these, do these have anything in common? These just have a 3 in them. Okay, tu cross tv. You can get all the scalars out. So I have a 3 and a 3 sine v. That's 9 sine v. And then I can do the determinant of the matrix that gives me the cross product. Here, put tu in here. So I have minus sine u cosine u 0. And then get the tv part in here. Cosine v cosine u, minus cosine v sine u, and minus sine v. To get this determinant, I'm going to copy down the first 2 columns. Are you just annoyed? Maybe you're just annoyed. It's really too bad. This is like, it's like opening up a magic potion and like showing you the ingredients. But maybe you're just annoyed. I don't know. I think you should think this is power. Anyway, the forward way, I get minus cosine u sine v in the I direction. In the j direction, I've got nothing. In the k direction, I've got plus cosine v sine squared u. Going the other way, in the k slot, I've got minus cosine v cosine squared u. In the I slot, I've got nothing. In the j slot, I have minus, minus, minus. So it's going to be minus sine u sine v. I've seen this before with the sine squared and the cosine squared, and the fact that these don't have the same sign means that I messed something up. So let's try to find it. Okay, this one should be plus. Okay, this one should be minus. That's bad. So one of those signs is incorrect. The u partial derivative should be negative, positive, 0. Negative, positive, 0. The v partial derivative should be positive, positive, negative. So here's my error. The v partial derivative should have positive here. That means this should be positive, and this should be positive. So let's see which ones that affects. Forward, forward, and forward. So this one should have a minus. And then backward, backward, and backward. It didn't affect this one. So now these actually add up the way that we expected. In the I slot, we've got minus cosine u sine v. In the J slot, I've got minus sine u sine v. And in the K slot, these add up to 1, so I have minus cosine v. So this is Tu cross Tv. What are we doing with Tu cross Tv? Well, we are dotting it with F. F is the vector field, the velocity of the fluid, and it's 2x, 2y, 2z. Two x, 2y, z. Okay, you should notice that this is kind of messed up. X, y, z, u, and v are all in here. We're trying to do the integral with respect to u and v. So I actually want x, y, and z all in terms of u and v. This is the place where students always get stuck in line integrals and surface integrals. It's like, you've done a bunch of work, there's too many variables, just what? What did I do? What? Well, when that happens, your parameterization is actually telling you what x, y, and z are. This says, here's x, here's y, and here's z. So x is actually 3 sine v cosine u. Oh my gosh. Y is actually 3 sine v sine u. And z is actually 3 cosine v. Here's a scalar. And here's a vector. This better all add up to like 2 at the end. So this scalar is just going to survive the dot product. Let's do the dot product though. The x coordinates multiply together. I've got minus 6 cosine squared u sine squared v. The y coordinates, I get minus 6 sine squared u sine squared v. And in the z coordinates, minus 3 cosine squared v. So what happens here? That's not a vector. If I take sine squared v out of these two, I get just minus 6. So I think I have 9 sine v minus 6 sine squared v minus 3 cosine squared v. This is not awesome. Nothing much else, there isn't much else good that happens here. So we'll just factor out the minus 3. I guess you could do a sine squared v plus a cosine squared v equals 1. So you'd have 1 extra sine squared v and a plus 1. But I'm not doing this integral by hand. So anyway, what does the flux equal? The flux is the integral, double integral. We're in the u and v mode here, and we have our bounds for u and v where the parameterization was. So u goes from 0 to 2 pi. V goes from 0 to pi. And the thing we're actually integrating is minus 27 sine v times sine squared v plus 1. Wait, v didn't go from 0 to pi. V went from pi over 2 to pi. I'm not doing that integral by hand, so we'll ask a calculator to do what it's good for, to do the thing it's good at. It's the integral from 0 to 2 pi, and then the integral from pi over 2 to pi of minus 27 sine v sine squared v plus 1 dv du. So I've just written the whole thing down. If you need to say pi to Wolfram alpha, it's slash pi. Subscripts are underscores, superscripts are carets. And this will just give us some answer. This is the amount of flux through that hemisphere. That is not what I meant. I wonder if it won't be able to do it with V and U. Oh no, it figured it out. Cool, so it's minus 90 pi. What are the units here? Well, this should be the amount of the stuff that's going through the membrane. So we've got a number of kilograms per second. So the final answer here will be 90 pi kilograms per second. Okay, this section was crazy long. It has like 2 hours of videos and 11 pages of notes. What are the takeaways from this section? The takeaways from this section are we can do surface integrals of a function, and we use that to do things like finding the mass of a curvy surface. And then we can do surface integrals of a vector field, and we use that to find the flux through a surface. In the flux case, we had two nice formulas that let us actually calculate these things. One of them was... Where are the formulas? This was where we came up with the idea. This is where we calculated the easy formula. Well, this is one of the formulas where this is them. Where if you have a parameterization of your surface, you need to find Tu cross Tv and do an integral that has a dot product in there. The second one is if you can get your surface defined explicitly in terms of a function of x and y, then you can use this second form. In either case, you need to remember that what you're doing when you find a flux integral is you're finding out how much the vector field agrees with the normal vector to the surface. Because that way, if the wind is blowing into the sail, then the wind will agree with the normal vector. So that's what dot products do. So f dot n is calculating how much f agrees with n, and that finds the flux through the surface. Do some calculations. Focus most on the setups. This is the setups are the parts that are really matter, even though we end up spending the most time on like the calculations. And then send some questions to your instructor and just don't give up. We've got 2 more sections left in the class, and they're awesome.